Okay, so again, a rational function is simply a ratio of two polynomials, p of x and q of x polynomials. To be a polynomial, it sounds a little deceptive because poly means many, right? But you could have like x over x squared minus 16. That's still a polynomial, even though you only see one term in the numerator, for example, 2. The bottom line is that it's going to be of the form a times x to the n power plus dot, dot, dot. That's a polynomial where n is a whole number. So you can't have a negative exponent, because if you do, then actually it would be rational itself. Or if there's a fraction exponent, it'd be a radical. That'd also be kind of weird. So it has to be a whole number exponent next to each variable. That's what makes it a polynomial. So it's a ratio of two of those. So x squared minus 16x plus 4, blah, blah, blah. Now find the domain. That's going to be the valid x values. We know this, right? When you have a rational function, what would make x not valid? What are some of the things that we need to keep an eye out for? Definitely, why -4 is bad? Yeah, so you don't want valid x values. So denominator, thanks, Kyle. Yeah. The denominator cannot equal 0. Very important. The denominator cannot equal 0. So x cannot equal -4. Now, the way we say it formally, probably in algebra 2, your teacher might have been cool just saying all real but -4 or something like that, or in middle school. But as we move on to calculus, you have to be proper. So we have to write an interval notation. So you write it like this. Why the parentheses? Why not a bracket? Well, why parentheses on -4?
It's -4, it doesn't work.
It's not included, exactly. If you include it, you put a bracket. And also infinity, I don't know what infinity is. It's some abstract idea. So no brackets here at all. And the U means union. It means you're uniting both sets. So that we can do this a little more quickly. Where are the x values that are not cool here? Plus or -4, right? So yeah, it's a little longer to write, but so be it. That's what we do. Just got to write it and deal with it. Oh, sorry. That was stupid. Because 4 is also not good as well. Okay. And now here, can the bottom ever equal 0, for example, 3? As a real number. Is there a real number that makes the bottom 0? No, right. Because if you try solving it, here's what's going to happen. Plus minus 4i, which that's not real, right? So I'll just kind of remove that. So in this case, what will we say your domain is? All real. Yep. You got it. All real numbers. Okay, vertical asymptotes. The quick and easy way is really whatever makes the bottom 0. So whatever makes the bottom 0 is the way you can think of it. However, it's a little deceptive. Like in the case of example 1, right? Let me actually graph example 1 for you guys so you can see what happens. X squared minus 16 over x plus 4. So let's go to Desmos. Y equals parentheses x raised to the second power. Sheesh. Divided by x minus 4. Was x minus 4, x plus 4. X plus 4, my bad. But it's a line, right? Now, if I move to -4, notice the hole appears. It says undefined, because you can't plug -4 into the original equation. But if you do simplify it, after you simplify, what happens to the x plus 4s? They cancel even with x minus 4. That's why it looks like that. So really what you need to do, hold on, let me go back to my notes here, is recognize it's not just what makes the bottom 0, because that's a little deceptive. It's really called, and this is the kind of the calculus explanation, it's really called an infinite, and I really want you guys to write this down, especially the juniors, if I teach you calculus next year. I do expect to know this. And we'll drill this into you guys. And your college professor will expect you to know this too if you're in calculus in college. It's called the infinite discontinuity. Why do you think we call it that? Think about this play on words, right? Infinite discontinuity. So you guys have noticed it's a dashed line goes up and down, right?
Why the discontinuity part? What does it mean to not be continuous? Is there a break in graph? Yeah. Fully. Is it breaking graph? Absolutely. There's something on the other side. So that's breaking graph. And why the infinite part? What's happening to y to get closer to the first asymptote? Where's y going? Keeps going up or down. So there's an infinite nature to it as well.
That's why it's called that. So what happens is that, and this is the part that's a little, kind of seems like Greek a little bit. As x approaches a certain number, so as x approaches a from the right side. So in layman's terms, so these are both the same thing. Let me get highlighter because it's hard to circle here. So let me highlight this in red, and let me highlight this in green. Those are exactly the same thing, just so you know. Those are exactly the same thing. So
whether you say it in red or green, it's exactly the same thing. Now, what does it exactly mean?
In words, it means this. And this is part that I swear to God, college professors, they do not explain this. They just it's just that's what it is, and just move on. And you're like, huh? Like what the heck happened? They're not very clear or transparent about it. Here's what it means in layman's terms. It means as x gets closer to a from the right side of a, y goes towards positive infinity. Okay, that's a lot of words, right? That is, let me move it so it's a little more clear. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 words. Oh my God.
I would much prefer, right, when x approaches a plus f of x equals infinity. I'd rather much prefer write that. It's kind of like a code in a way.
So that's all that's happening. That's what it means. This is the approach you have, no pun intended, sorry. But that's the approach you must have. So we're talking about approach, right, with asymptotes and limits. When it comes to vertical asymptotes, you have to think of it that way. Don't think of limits on zero, because then you're not understanding. You have to have this deep understanding as we move on to calculus, because calculus is all about change, how things are increasing, decreasing, and whatnot. And you start applying it to actually real life problems that involve change, like money, like if you're in health, like with COVID, like we saw how things are changing and the flattening of the curve. That's all calculus, by the way. So that you have to use to understand that stuff. So anyway, we have to have the understanding. That's what's happened there. Okay. So let's now talk about this. Domain. Yes, the quick and easy way will make bottom 0, but really what's happening is as I get close to 3, y is going to go haywire. So x cannot equal 3 here. So domain is this. I mean, we're just going through notes now, just to know. Yeah. The vertical asymptote is x equals 3. And it's not so much because it makes bottom 0, even though that's a quick and easy way. It's really because as I get close to it, it's going to go crazy. So if I were to do, oh, by the way, there's also a horizontal asymptote too, at y equals 0. I'll explain that in a little bit too. If I make a quick table, if I plug in, say, goodness, you guess what I did wrong? Yeah, it's okay. How did I catch myself? So I was gonna start plugging in numbers. I was gonna plug in like say 2. I was like, wait one sec, I'm all the way at -3. So I caught myself by making a table. You have these little stop gaps. Prevent those careless errors. So make a table is sometimes good. I can do a sign chart, but I'll just do a table instead. You need those stop gaps in place. So yeah, so let's plug in 2 and 1 and 4 and 5. If I plug in 2, I should get -1. Plug in 1, I get -0.5. Plug in 4, I get 1. Plug in 5, I get half. 2 comma -1. 1 comma -0.5. And then 4 comma 1. 5 comma half. Bless you. There you go, right? So what is y doing as I get to the right? So think of it this way. As x approaches, we'll put a 3 there and a 3 there. As I approach 3 from the left side, right?
What does that mean? Let's approaching 3 from the left side. Give me an example of what X would be. If we're approaching 3 from the left side, like 2.99999, exactly, right? I've got 2.99999. What's Y going to do when I get closer to 3 from the left side? Just shooting down, right?
So think of this as X being roughly like 2.9999 and so forth. So that's going to be negative infinity. Now, what about from the right side? What could X be? Like 3.0001? That's positive infinity. Right? Okay. I was pushing 3 from the left side, it's going down forever. Pushing 3 from the right side, it's going up forever. Now, the end behavior, that's a horizontal asymptote. By the way, you can cross. That's a Z, by the way. Sorry. That can be crossed. In this case, it's not, but it can be. So don't think it can't be. A lot of people think that because they see these and they kind of make that assumption. I know no math teacher says that. I'm pretty sure the middle school doesn't say that either here. The middle school math teacher said middle school, they should probably get some training. That's not right. As X gets really large towards the right side, what's Y doing?
Is it flattening out as it gets further to the right? What's it flattening out towards? But what Y does it approaching? 0, and Y goes the other side. So it's 0 in each case. Yeah.
So that's a horizontal output end behavior. And you think of like a limit as X approaches positive infinity. That's what we call ends. You're looking at the ends of the graph. Okay, so I kind of dissected that as much as I could. Now let's do this more quickly. And I'm just going to kind of give you the graph. Just trust me, these are the graphs look. I trust you guys can figure it out by making a table or going to Desmos. And totally cool, guys. If you have to go to Desmos initially, that's totally fine because you got to learn how to do this. But ultimately, you can't use Desmos. By next week, you can't. You have to actually know how to do these by hand. But those are your asymptotes, and the graphs are going to look like this. For example, I put in like 1, I get -1, or -1, same thing. If I put in like half or 1/4, it just gets more negative. If I put in like 10 or 100, it gets more closer to 0. So domain's all real except 0. We know this. Can't do 0. Vertical output X equals 0. These both go towards negative infinity, and these both go towards 0. Once you get the hang of it, you do it in like 10 seconds. I touch it over minute 2. I just about 10 seconds. Once you know how the graph looks, this is easy. It's not hard, right? And why does this graph look like this? Because you have negative. Can X squared ever be positive, by the way? Sorry, can X squared ever be negative? No. X squared is always positive. You do -1 over that, so overall it's negative. And of course, as you get more closer to 0 for X, Y goes haywire, goes down forever. Question on that one? No, let's keep moving. All right, find the vertical asymptote, state the so what I would suggest that you do always is factor and simplify. Why? That's because if a factor cancels, it's a whole, not a vertical asymptote. We'll talk about holes in just a little bit and how they differ from vertical asymptotes. Because remember, vertical asymptote has to have this situation where you get closer, Y is going up and down. For a hole is literally that. It's called a point discontinuity because it's a break, but it's a point removed, or removal discontinuity, removing a point. We'll have that discussion just a little bit. But yes, you have to cancel out factors. Very, very important. I mean, I can factor this, but nothing's going to cancel, right? So what values of X are not cool? Totally, 100%. Thanks, Tammy. So yeah, you have this. And yeah, it's just going to be X equals -3 and X equals 3. Okay. Here, let's factor again. Shoot. I don't think anything's on. Yeah, so it's going to cancel, but it's not. Yeah, because you have 2x plus 5x minus 2. I think that's correct. I did it by trial and error. If you have other techniques for factoring, totally fine. If you need help factoring, let me know. I'm not going to spend too much time on that, but sometimes you can do trial and error that could work. 2x, 5x minus 3. I think I did it right. Yeah, nothing cancels. So x equals negative 5 halves. And x equals 3. Those are your VAs. And all real except negative 5 halves. Yeah, that. There we go. Questions? We good? All right. So, yeah, so something called a hole, which more formally we call a point discontinuity. Or you could call it removable. Some teachers call it removable because you're removing a point. Okay. So find x, y intercept all vertical clouds associate any holes. Well, they're none here. We already know. I don't know why we're doing this again. We already know it's this, right? That's easy peasy. Here there are none. And how can you tell when a factor cancels out? Which is actually said in the fine print too. That's how you can tell, because what's going to happen is that as you approach that x value, y is going to be going towards a certain number, not infinity or negative infinity, but towards a certain number instead. We'll see that with one of the problems, I'm sure. I will put these notes in advance, but I should. X-intercept is 0, 0. Y-intercept is also 0, 0. Remember, here you plug in 0 for y. Sorry, 0 for x. Here you plug in 0 for y. Or the numerator has to equal 0. Right? Because the numerator is 0, the whole thing is 0. Because you put 0 over here, because fx is y. Once you have that, then you can do the graph by making a table and putting all these other things in place. Any questions? We're good? Yeah, cool. All right, great. Let's keep moving. Horizontal asymptotes. What's happening with that? As I already mentioned, I know it's kind of cryptic. You have like all this like mumbo jumbo, and these are exactly the same thing. Just as I said before. This in red and this in green are exactly the same thing. So, in layman's terms, what does it mean? It basically means as x approaches positive infinity, or you do negative infinity, if it's that case, y approaches the value of b. Yeah, it's a lot of words, right? Just condense and write it in limit notation, or as x does this, fx does this. And you do it for negative infinity as well, just so you know. You can also do it for this limit as x approaches negative infinity of f of x equals something. You could do that as well. By the way, you could have 2 horizontal asymptotes. That is totally possible. That is totally possible. You can't have 2. You guys know how you can have 2? Does anyone have an idea? Want to take a stab or guess? I can have 2. Was that? Not a whole not so much. No. What piecewise functions? I'm not sure you guys do you guys do? Actually, I don't think we do in algebra 2. Do you guys remember doing piecewise, or do you guys do piecewise functions with Mr. Gilmore? Maybe. I know there's a lot of transition last fall. Like these kind of things here. You have 2 different functions. If x does this, yeah, you could totally have like two different graphs where they march their own beat. You totally could have that. There's no type of function which I don't think we discussed called a logistic function, where it kind of does this. It's actually a more accurate graph when you're looking at like contamination, like COVID counts. Like let's say someone comes here with COVID and gets everyone sick, so it increases is a quick spike. But ultimately, does it keep increasing? No, because you reach the limits. What's the limit going to be? The number of people on this campus, right? So that could have two horizontal asymptotes, but I don't think we're going to talk about that kind of graph, so let's not worry about it. Generalizations, which I kind of cringe when I do this, because what happens is that you guys then memorize, and then on like a day before test or on the day of a test during office hours, like, wait, which one is it? NM, blah, blah, blah. I'm like, dude, no. Just look what happens to Y when X gets big. That's all it is. And actually, this is reversed in the way I do it. I usually put M in the numerator and the denominator. So maybe I won't even talk about the way I see it. But I mean, the way I put M and N. But regardless, this is all about what Y approaches as X gets super negative or super positive. That's it. That's all it ever is. Yes, there are generalizations. Yes, we say this. We call this bottom heavy. Why do you think I'm calling that bottom heavy? If n's less than n.
N's the exponent is the highest. By the way, these are the highest exponents. These are the degrees. But I think they said, yeah, the degrees. If the degree of the bottom is higher than the top, why can't find the bottom heavy? Because it has more impact, right? It has more impact than the top does.
This I call top heavy, because the top has more impact than the bottom does, because the top is a higher exponent. And this is kind of like even in a way, because they're both the same degree. So you just take the ratio of their coefficients. Think about it. 3x and x, 5x squared plus 1. Let x equal 100. What would happen? You have 300 over what? 50 thousandths plus 1. What?
Someone offers $300 or $50,000, $50,000, right? So yeah, you see how as X gets bigger, does the top ever catch up to the bottom? No, it trails. So overall, what is this fraction get closer to? As X gets bigger, what's getting closer to this fraction overall? What value? 0, exactly. That's why it's 0. And you see this case when you see the denominator for the higher degree than the top, it's going to be 0. Let's do this one.
11th example, throw it off to the right. Let x equal 100. What does the top become? Top becomes 1,000,000. You have 6 zeros. What does the bottom become? 10 thousandths. Sure, that gets big. Minus 200 plus 9. But guess what? What's much bigger?
The top or the bottom? The top. The bottom never catches up to it. There's going to be a separation. It's going to pull it back. So in this case,
the horizontal asymptote here is y equals 0. Here, there is no horizontal asymptote. And then these increase the same way. If I let x equal 100, I have 60 thousandths over 30,000 plus 7. Overall, what does that fraction become overall?
closer to what? What do you guys think? Does that 7 matter so much when this gets bigger? Right, the leading terms can go top, bottom, dominant, right? So overall, what do you think this fraction is getting closer to? 2. Yeah, it's getting closer to 2. Yeah.
You just take the ratio of the coefficients, A over B. Now, the thing that sucks about example 11, there's going to be what we call an oblique asymptote, which I kind of talked about last Friday, but I had to kind of gloss over it. Or we call it slant. It looks slanted. To find these, you have to do long division. Which, by the way, we do have a quiz today. I didn't forget. We have a quiz today, so I'm going to make sure you guys have time to do it. I'm actually going to review how to do the quiz before we take it. So we'll start in about 10 minutes. So I'll do a little review beforehand. because there is a long division question on there. And I did put in school G. There's a long division question on there. Because you have to do it, unfortunately. Okay. I think we're almost done with these notes, so I feel better about this. And we're just going to do a lot of practice tomorrow on this stuff. On this, we'll do a lot of practice. So here we go. This came from this. And these canceled, so you end up getting this. So the vertical asymptote is x equals 5. The horizontal asymptote is y equals 0. That's because the bottom is a higher degree than the top. The whole, because x plus 3 canceled, because it canceled out, you plug in 3 into the simplified form, and it's negative half. So it's 3 common negative half. No, sorry. I was not supposed to plug in 3, guys. What am I supposed to plug in? Negative 3. Right? It was negative 3. Negative 1/8. My bad. So whole is going to be, gosh, like a stylus. Here we go. The domain is still, you have to exclude negative 3 and 5. Even though negative 3 is not a vertical out, so you have to exclude it. You have x equals 5. Horizontal asymptote y equals 0. Make a quick table. You just assign Charles to a quick table. If I plug in 6, I get 1. If I plug in 4, I get negative 1. So I expect the graph to look like this. You let the asymptotes kind of guide the graph. The end behavior is 0 in each case. So there you go. So again, why is negative 3 not a vertical asymptote? Because the limit as x approaches negative 3 from either side is going to be negative 1/8, not infinity.
This function does not approach infinity like 6 goes to negative 3. If it did, it would be a vertical asymptote. It's because it approaches the number. So that's a key difference
Between the two. The key difference, and by I am recording, so I know I'm giving you guys a lot of information, so you should rewatch this, and I'll talk about it again tomorrow, between a whole and a vertical asymptote, is that y approaches a certain number when x gets close to the whole, but y approaches positive or negative infinity when x gets closer to the vertical asymptote. I just ran out of space. Gosh darn it. Kind of like there for now, so you guys can see it. So the key difference between a whole and vertical asymptote is that y approaches a certain number as x gets close to the whole. Y approaches positive infinity when x gets close to the vertical. That's a key difference between the two. Just so you know. So now we're starting to see the numerical aspect of it, the graphical, and somewhat algebraic as well when things cancel out. So when all those things are intertwined, right, that's when this starts making more sense. You kind of need to do that to be successful in this class in calculus. You have to be able to see all 3 modes. Numerically, what's happening? A, when x is close to this number. Algebraically, things cancel out, don't cancel out. And graphically, how it looks in the graph. So once you see all those interconnectedness, the learning becomes rich, right? Okay, questions on that for our... No? Okay. We're good? Yeah, okay. The oblique asymptote. Okay. Oh boy. Actually, this is great. This is great review for the test. Sorry, the quiz. Sorry, not test, quiz. Because you have to do long division, unfortunately. You have to do long division to get it. I know it sucks.
Synthetic.
You can't do synthetic because x squared at the bottom, unfortunately. If it was x plus 1, go synthetic. Totally. I fully agree with you. Okay. What do you multiply to x squared to get to x cubed? X. Then you multiply all this by x. And you stack them like this. And you put a minus like that. And you subtract. I put the parentheses so that way I distribute negatives correctly. So you bring down a negative x squared. X cubed minus x cubed goes away as it should. What's 7x minus x? Yep, and bring down the negative 8 as well. Okay, what do you multiply to x squared to get the negative x squared? Yeah, minus 1. So you multiply all this by minus 1, which is negative x squared minus 1, and you subtract again. Those go away. You get 6x minus 7, because you're doing negative 8 minus negative 1. At this point, x squared doesn't multiply to 6x. That's your remainder. So you put plus 6x minus 7 over x squared plus 1. So I'm going to get a highlighter here. This and this are the same. These are the same. A lot of people don't realize that. They are the same. If you actually graph both of them, you would get the same thing. These are the same. So why do we do this then? What's the whole point?
Slant asymptotes. This is what happens when x is really large. Okay.
So for a slant asymptote or oblique, what you want to do is consider what y does when x approaches positive infinity or negative infinity. Well, think about it.
This fraction here. What denominator is what degree is higher? The bottom or top? The bottom. If x gets really large, let's say it's 16 minus 7. That's 10,000 plus 1. What happens with fraction that x is large? This is 0. Think about.
Yes. When x gets large, that goes towards 0. So what are you stuck with? Y equals x minus 1. That is your slant asymptote. That's why you do the long division. So you can look at the remainder and say, well, that just goes away. I'm focused on what's left, x or what I got, x minus 1. So the graph behaves like that. Let me plug this into Desmos so you can see a little better why we call it that. Okay. So x raised to the third power minus x raised to the second power plus 7x minus 8 divided by x raised to the second power plus 1. Let me clear. And let me graph y equals x minus 1. Look at that blue line and look at the red curve. In the middle, they don't look the same, right? Do they look the same as I go further to the right? Yes. Do they look the same as I go further to the left? Yes. Are they exact same? No. Or are they pretty close? Yes. That's why we do the long division. This is the reason why we do it. I know it sucks. It's not a great process, but you got to do it to understand these graphs look. Why do we care these graphs look? Because things are modeled. There are a lot of things you don't know this in science, engineering, whatever, STEM, or even business applications by econ. I think half you guys might major in econ. I don't know. A lot of things are modeled using rational functions. You have to understand how these behave if you're going to apply calculus principles to them. And why do they have the slant asymptotes? Because of the long division. That's the reason why. So there is a reason for it. Trust me. You'll thank me and an alumni event or something. Yeah, Mr. That really made sense. Thank you for explaining it to me. Or maybe you'll forget. I don't know. But bottom line is you have to understand that. And there's also this technique is used in another calculus principle, which I don't want to talk about. It's not going to make sense. But this technique of long division, you have to use for another calculus thing later on as well. So it's not a fun process because it's easy to make careless mistakes, but you have to do it, unfortunately. So I have to teach it. because trust me, if I do teach calculus, I want you need to know it. So I'm not going to do the last one because I think just in the interest of time, I think we're good. But I already showed you the long divisions. I'm happy about that and got part of this. We can finish page 6 tomorrow. That's fine. Homework, what I'll probably have you guys work on is actually there's actually homework for this. It's homework 48. I think it's just 4 graphs, which I think you guys can totally handle. Yeah, so I'll have you try this. If you get stuck, it's fine. It's okay. And then we have the classwork as well, which we'll do in class tomorrow. And if we did the first 2, we have 5, and it probably each one might take you about 6-7 minutes, probably. So this is going to easily take our time tomorrow as well. And then I'll have a review ready by Friday. And then we'll have another review day on Monday, or sorry, Tuesday, and then test will be Wednesday. And if anyone's leaving early for spring break, let me know. We can bring something. So we'll start the quiz now. I just need to go grab it. Okay. Oh, no worries. I'll record it. You're good. All right. So let me go ahead and stop recording.